Hello everyone, this is the first lesson from Microwave Cafe. I made this channel to upload my videos in the design of RF and microwave circuits. I want to honestly be more practical in my videos than just talking about the theory of design of circuits that you most probably hear in your classes. So I'm going to show you how to design passive and active circuits. Okay, let's get started with the first lesson. I made some slides as introduction of microwave. First, let's take a look at them. I am going to talk about some transmission lines, FR4 boards, some parameters in microwave that we care, 50 ohm standard, examples of 50 ohm ports, scattering parameters using LineCalc in ADS, and simulation of a 50 ohm microcircuit line in ADS. Okay, I try to provide the references of what I'm using in my slides so you can follow that if you want more information. Some microwave transmission lines. This is a coaxial cable. As you see, there's an inner conductor, there is an outer conductor, and there's a dielectric here. If you want to synthesize this coaxial cable to know what's the impedance and what's uh, the phase that this coaxial cable is making, um, so you just need to know the diameter of this inner conductor and diameter of the outer conductor, or vice versa. You have these two diameters and you have epsilon r of this uh, dielectric, so you can calculate the impedance and the phase difference that is making. There is another structure. Let me talk about this first. A macro strip line. So you have a line here. You have ground, a ground plane underneath. There is a dielectric between these two lines, and the height of dielectric is called h. And the dielectric has epsilon r. Uh, so you need to know the width, the length of the line. You need to know the height of dielectric and epsilon r of dielectric, so you can calculate the impedance that this line is generating and the phase difference that this line is generating. The other structure is coplanar waveguide. You see, this is our substrate with a height and epsilon r. We have one ground here, we have a strip line here, and we have another ground here. The spacing between these two and the width of this strip line is defining, and also h, of course, and epsilon r, defining the impedance and the phase of this structure. The next structure is coplanar waveguide with ground, or CPWG. The other one was CPW. So in CPWG, just consider you have a CPW. Just add a ground plane underneath of it, and you will have a CPWG. Okay, FR4 board parameters. So basically there are different type of boards. Let's say Rogers that has a very good loss tangent. We have FR4 that is the cheapest almost, and it's good for students. I used to use this board a lot in my designs. So we have some parameters. The way you can find these parameters, you can just Google it, FR4 board parameters, characteristics, and it will show you these values. Uh, Relative permittivity, or epsilon r of FR4 is 4.4. Relative permeability of FR4 is 1. The substrate thickness, so there are different thickness for this substrate. 62 mil or 1.57 millimeter is the cheapest. That is good for students. Uh, Metal thickness, we are going to consider 1 ounce of metal, uh, basically the thickness of this metal. And so it's 1.5 mil or 0.038 millimeter. the conductivity of metal, so it's copper. So the conductivity of the metal is conductivity of copper is 5.857. And dielectric loss tension or dissipation factor or tangent D, it's approximately 0.02. Okay, so we know parameters of this board now. Then some important parameters in microwave. Um, Frequency for sure. At what frequency you're designing your circuit. Let's consider 2.4 for all our designs unless I mention it's uh, Wi-Fi frequency. Characteristic impedance. It's Z naught. So far, probably in theory, you have heard of Z naught is the characteristic impedance of each line. Uh, so we have width of the line and length of the line. This is the width of a line and this is the length of the line. Effective electrical length of the line or the phase difference that a line is generating is beta L. What is beta? Beta is phase constant. L is the physical length of the line, this length. So if you multiply beta by L, you will calculate effective electrical length, which is equal to beta, basically 2 pi over lambda, and lambda is the wavelength. Basically effective wavelength if you have a dielectric that epsilon r is not epsilon 0. So let's look at an example. So we have a microstrip line here and we want to calculate how much phase difference or basically effective electrical length of the line. How much is that? We use this equation a lot in our designs. If we assume that the length that we have is lambda over 4, just you can calculate it easily. What is lambda? And you put lambda over 4 in this equation instead of L, so we will get 90-degree phase difference. What does that mean? That means if you have a macrostrip line, the length of the line is lambda over 4. This line is generating 90-degree electrical length or phase difference for you. 50 ohm standard. So it's important to follow a standard in labs when we are designing our circuits. When you have an antenna in US, mostly in most of the other countries except England, that they use 75 ohm, we use 50 ohm standard. So that means when you design a circuit, unless it's specified, so we use 50 ohm. You design an antenna, you just cut it from here, you connect it to the device that you can measure your antenna. This is a PNA, a network analyzer. And so the input and output, or 2 ports basically of this device that is for measurement, is 50 ohm. You don't want to have any mismatch. So you design 50 ohm, you cut it, you connect it here, and you can measure it, the parameters of your design. If one is 25, the other one is 50, you will have a mismatch. And so what you're measuring is not correct. Also, if you have a 50 ohm standard, you can connect it to the other circuits. Inside of circuit, it can be any impedance, but when you're at the port, at the output or the input, doesn't matter, you need to follow 50 ohm unless in some specific situations that, for example, some LNAs, sometimes you don't design for a good input match, and sometimes you do, but we will talk about them later. But generally accept this for me, that we need to design with 50 ohm standard to be able to measure whatever we are designing in our lab. Okay, now we have a circuit. Assume this is the board, and how do we measure it? So we need some ports like this one, and this one, some SMA connectors to connect to our circuit to be able to measure. We said the input and output of our circuit is 50 ohm. So if we don't want to have any mismatch, we need to have a SMA that is 50 ohm as well. So you assemble this SMA to your board, and so you will have a good match, and you can measure it easily. The same thing here. This is our board. This is 50 ohm, and here is 50 ohm. So we connect it to two SMAs that they are 50 ohm. The next slide is about scattering parameters. I don't want to go through the theory of S parameters. I just want to let you know that parameters are parameters to evaluate performance of an RF or microwave circuits. In lower frequencies, you just measure voltages or currents or some other parameters. Here, we have some new parameters that they are defined and you probably didn't see before, and they are called S parameters. And we evaluate our circuits with them. So if you consider we have a circuit or we have a system, it has two ports, one port P1 input and the other port is output P2. So when we say we have a good matching, S11 in S parameters needs to be better than minus 25 dB when we are designing it. Because when you are designing it, normally there are some parasitics in measurement, and this minus 25 will drop to minus 20 dB. That's what we say in circuits we accept the value, at least for the circuits that right now we are designing, which are macro strip circuits. But when you go toward more advanced circuits, it's much harder to get to minus 25, and you will be more narrow if you want to get a better S11, which is better than minus 15 even, and it's harder. You will have a more narrow band, and we don't want that. Okay, so for this course, which is macro strip design, we will consider in our designs, we want to have better than minus 25 dB. And the same thing for S22. When we have a port, the output match, we say we have a good matching for output when S22 is better than minus 25 dB. We have S21, which is forward transmission coefficient. That will define a transmission, depends on the circuit that is active or passive that I will show you. So it needs to be negative or positive. And we have S12 that is called reverse transmission coefficient. Again, it doesn't matter if we have a passive or active circuits, S11, S22, that there are some criteria for matching. We say they need to be better than minus 25 dB. But S21 and S12, I don't give a number to them yet, and you will see how much they are later. And finally, LineCalc in ADS. So I will show you how to do that, but let's just very quickly go through it. So we put the parameters of what we had for FR4 here. We put the frequency here, and we have two approaches. One, you have the width and the line of your circuit, your line. You want to see how much characteristic impedance is making and what's the phase difference or electrical length that is generating. So you analyze it. And once you have these values, you want to see what physical values of W and L you will need. So you push on this and you synthesize it. It will give you the W, the width and the length of what you need. Okay, so with all of these information, let's just get started with ADS. I want to show you how to use LineCalc. Here, after double clicking on ADS, you see the window here. You just click on this. We want to make a new workspace. I want to put the name as Lesson1. Okay, and we create a workspace. Okay, and so we want to create a schematic window as well. So we click on that, and I just leave the name the way it is, cell 1. We create a schematic, and here's our schematic. I want to pull up LineCal, the one that I showed you the last slide. So you go on Tools, LineCal, Start LineCal. You click on that, and this window will show up. Okay, so I want to enter the characteristic values of FR4. Epsilon R is 4.4, UR is 1. The height of the substrate is 62 mil. T, or the thickness of copper, is 1.5 mil, and conductivity is 5.87 E7. I am going to design at 2.4 gigahertz. Okay, let's take a look at here. I want to synthesize. I want to say I have a line that is 50 ohm and it's generating 90-degree effective electrical length. So I want to see that if I want to generate such a line, what is the width and the length of the macrostrip line? I need to click on synthesize, and it will give you 116.82 is the width and length is 671.72 mil. Okay, I want to implement this and verify it. Okay, let's do that. So this palette is where you have most of your things, and you pick the items from here. I want to go to the T-line macro strip. I scroll down T-lines macro strip in this window. What I need is a macro strip line. But before that, I prefer to go and use an ideal one just to compare. Okay, so no macro strip yet, but just an ideal T-line. So here is my T-line here. I just clicked on that, I put it on the screen, and I push escape key. Okay, and I want a simulator for this. So the characteristic impedance of this line is 50. The effective electrical length is 90-degree, and the frequency, you click on here, you push 2.4, and it has gigahertz unit. I want a simulator. Okay, let's just go and pick simulation S parameters. That's what I was talking about. You click on SP here and you put it on this desktop. You push escape key. You click on terminal. This terminal is like a port that I was talking about, and one here, and you push escape. These two terminals are open now. We need to connect them here and here. So we click on this connector, basically inserting wire. I click on this side and I click on this side, and this is connected. The same thing. This side and this side is connected, and I push escape. Here is ground. I click on that I put one here, and I put one here. Okay, escape. Now look at this. This is like a two-port thing, what I was talking about. Let me see if I can put a shape here like this. This is exactly a two-port thing that I was talking about. Okay, you don't need to put this shape. Just, I wanted to just make it similar to my slides. Okay, the next thing here, I need to define where is the start point of my simulation, where is the stop point, and what's the step. If we want to simulate at 2.4 gig, I will go 0.4 gig lower and 0.4 gig higher. So I will go 2 gigahertz to 2.8 gigahertz. The steps, I will go with 0.01 gigahertz. Okay, it's ready. Let's click on simulate here, which is this gear. Okay, this is data display. It will show up. So you need to define the parameters you want to plot. What do I want to plot really? So this is a port 50 ohm, this is a port 50 ohm, and this is a 50 ohm line with electrical length of 90 degree. Let's see if it's really 50 ohm, because this is from here we are seeing 50 ohm, and from here we are seeing 50 ohm. So these guys, they need to have a good match. That means S11, which is this port 1 input matching of this uh, box. S11 needs to be better than -25. S22, the same thing, needs to be better than -25, because this is 50 ohm, this is 50 ohm, so good matching at the output. And the effective electrical length needs to be 90 degree based on what we have here, because we don't have any other component to generate phase difference. Let's check it out. I click on this here and I put it here. It will ask you what you want to plot. I click on S11 and I click add. It will ask you what unit you want to plot. I'm gonna go with dB. And also I want to plot S22 as well. Add dB. Okay. And I want to plot also S21, which was the transmission, but I want to see the phase of this transmission. If you remember here, forward transmission, so the magnitude, the amplitude of this will show how much loss you have. The phase of this, though, it will show you how much your phase difference is, which here is our electrical length. So S21 add not dB, but phase. And actually you can add the amplitude in dB as well to just see what's going on. Okay, let's do that. Okay, after you pick all of these, I want to split all the windows. So you click on this. Once you don't do that, and see what happens, but I will do that. If you don't do that, it will plot everything in one square. You click OK. Here we go. I try to open it. I mean, magnifying it. Okay, let's see what we have here. So I expected to have a really good S11 in dB. Right now, it's really good. It's like imaginary, like you won't reach in real life to that. It's minus, like better than -300 dB. Imagine it's almost zero. S22, it's better than -300 dB, which means you have a great match at the output. And the phase of S21, look at that. We design at 2.4, okay? At this point, at 2.4, it needs to be 90 degree. Let's see if it is. How can I say that? I'm going to put a marker here at 2.4. So you click on marker, you click on new line, and you put it here at 2.4. So it says the phase is minus 90 degree. Okay, and my S21 in dB, because the line is ideal, so that makes sense that you don't have any loss, right? Tangent D is 0, so it's showing 0. And the other ones, because there are some breaks here, yeah, it's so good, so it's showing just invalid, but you can see that it's better than minus 300. Okay, now let's do something else. Let's just put a macro strip line there instead of an ideal line. How to do that? Just click on here. You go to T-lines, macro strip. Okay. Pick a macro strip line, M line. Put it here. Okay. And push escape. And you need to define the substrate for this. You need to tell the simulator that there is a substrate. So simulate based on that. So you click on M sub and you pick millunits or the one that you need and click finish and you put it here and push escape. You import the same parameters that you imported in the LineCal here. That one was just to know the width and the length. Here is to tell the simulator, simulate based on these values of substrate for this line. Don't simulate something weird. So H was 4.4. Epsilon, sorry, H was 61 mil. Epsilon R was 4.4. This one was 62. Conductivity was 5.87 E7. The thickness of metal was 1.5 mil. Tangent D of F44 was 0.02. That's it. Can we simulate it? Not yet. We need ports. The same as here. Okay. So again, let's just go here. Let's find simulation SPROM and scroll down. Let's see, where is our terminal? Here. We have a terminal here. We have a terminal here. Push escape and connect this here and this here. And then put one ground here and one ground here. Okay? Okay. Are we done? Not yet. Because we want to simulate a 90 degree with 50 ohm, which we have here. Based on the LineCalc, we need to import this width. We need to enter this value. I just copy it and I paste it here. Just simple right click, copy, and then paste it. And here I copy it, Control C, and I paste it here. Control V. Okay? Okay, are we done? What do you think? I say we are done. Let's save it and we can simulate it. Now, let's pay attention here. We had port 1 and port 2 here. So we had S11, S22, and S21. But here we don't have port 1. We have port 3 and port 4. So we are going to have S33, S44, S41, right? Based on these ports. Okay, so we won't be able to have two port 1 in one schematic of ADS. It doesn't let you to do that. Let's simulate. Okay, now that we have this, let's click again on this rectangular plot and put it on this white part of our page. And The same as we had here. We had S11 there. I'm gonna pick S33 here. Add it in DB. Okay. Let's pick S22 here. This is basically S44, right? Add it in DB. Okay. We have S21, phase of S21. So we are supposed to have phase of S43 to know electrical length. So 43 add not dB but phase. Okay. And the amplitude in dB of S21. S21 here is S43, right? So S43 again, add, and we want it in dB. Push OK. Don't forget to push this window so it will split all the parameters, and you push OK. Here what we have. So this one was with ideal line. That means no loss. This one is with a real macroscopic line. That means it will consider tangent D of your F4, which is 0.02. Let's put a marker there at 2.4 gigahertz. Marker, new line at 2.4. Frequency is 2.4. Okay. Let's see what is here. Let me divide my screen. What is my input match, which is S33 here? Right now at 2.4 is minus 39.92. Is it good? Of course it is good. It's better than minus 25 dB as we discussed. So we accept that. What is the output matching? Is it good or bad? The output matching, to know what it is, we look at dB of S44, and it is minus 39.92. So it's better than minus 25 dB. It's good. What is the phase that this macro line is generating? It is minus 89.58. It's very close to 90 degree, to minus 90 degree, right? As here we had minus 90. So here we have minus 89 point. So we were very close, right? And what is the loss of this line? The loss of this macro line is minus 0.13. Okay, so that's the difference between an ideal line and a real macro line. We see loss, we see not ideal return loss values, and we see a little bit off from the 90 degree. If you remember, I said that when the electrical length is 90 degree, that means the length of the line is lambda over 4. So I expect this to be lambda over 4. If you calculate it, you will reach this value. Okay, so far we learned how to simulate a simple line in ADS, and we learned how to work with this LineCalc. I recommend you that you a little bit change the values and see what happens. For example, very quick, if I change this 50 ohm, I want to make a mismatch to see how much my result will change. Right now this is 50 ohm. I'm going to connect a 10 ohm line, which is ideal, to 50 ohm ports. What do you expect? Definitely bad S11 and definitely bad S22. Bad means worse than what is showing right now, right? Let's simulate it here. I push on this and let's check it out. Yeah, look at it. It's terrible. In dB, it's not better than minus 25 dB anymore. So it's bad. It's showing that you have mismatch, right? And you have the phase difference of 1990 minus 90 yet, yeah, still, but also look at your loss minus 8.3. How this loss was generated when your substrate is not lossy? Actually, it's not loss. It's just a reflection of your wave because you don't have a good matching here. So the wave is coming here. It's not good. So it will go back. It won't radiate to the output. And the same thing from output to input. So that means you don't have a good matching when you have 10 ohm. Okay? Okay. This is the first lesson, and I will talk about design of a quadrature hybrid in the next lesson. Thank you for your attention.